Hello, good morning everyone. My name is Deepak Kumar. I'm a BTech fourth year undergrad student from IIT Mandi and my project partner is Akansha Bhaikar. Today we will be discussing a research paper whose topic is LLaMA with where image is worth 2 tokens in large language models, as you can see the authors here also. So today we will discuss this research paper. Okay, so let's start. Okay, so now we will discuss the problem statement. So before discussing this, let me begin by highlighting the main challenge of this paper, which it addresses. So vision language models or VLMs like BLP, Lava have shown impressive performance on image-based tasks like captioning and visual questioning answers. However, they face serious scalability issues when applied to videos, especially long ones. For example, if we take 1000 frame video and encode each frame with a 256 visual tokens, we end up with over 2.5 million tokens. That's far beyond even the largest language model can handle. This massive token count results in high computational cost, slow inference, and GPU memory overload also, which makes current VLMs impractical for real-world long video tasks. So methods attempt to solve this by using temporal compressions or query-based selection, which we will discuss further in the upcoming slides, which makes current VLMs uh, so that it neither lose important visual details or don't scale well. Okay. So the key problem is how can we represent long videos efficiently without sacrificing the ability to understand and respond accurately to user queries. Okay, so this is basically our problem statement. So let me phrase it once again also. So the key problem is how we can represent long videos efficiently without sacrificing the ability to understand and respond accurately to user queries. So this is the central challenge that LLaMA WIT aims to solve this research paper. So we will explore it, how it does that. Okay. Okay, so in this slide, we will discuss the solution proposed by this research paper. So it basically introduces a very simple but powerful idea representing each video into using just 2 tokens. One is context token and other one is content token. So what are these basically? So context token is generated based on the user's instruction. It helps the model to focus on the most relevant global information in each frame. And the content token summarizes the visual appearance of the frame, and the number of content tokens can be adjusted depending on the situation. So this dual token design drastically reduces the token count while still preserving the critical information. For example, a video that would normally require thousands of like hundreds of thousands of tokens can now be represented in just 2 tokens per frame. So the system uses a visual encoder to extract image features and a text decoder to generate the instruction guided queries. So these are then projected into this LLM embedding space and passed into language model like Vicuna to generate the response. So we can say that overall this research paper makes possible to process hour long videos, propose a solution to do this efficiently without losing the context or the content for accurate reasoning. Okay, so in this slide, we will discuss what basically this research paper brings us what to the table. Okay, so basically the research paper introduces the dual token framework where each frame is represented by 2 tokens, one per context and one per content as we discussed in the previous slide also. This drastically reduces the number of tokens as we discussed. Second, the context token is instruction guided. That means it's generated based on the user's query. So the model pays attention to only the relevant part of each frame. This improves the response query and the efficiency. And the third thing is the method scales to long hour videos. Thanks to the reduced token count, LLaMA WIT can process long video sequences, even movies, using existing LLaMA like Vicuna. Fourth thing, the author construct a high quality instruction dataset for training, including 9,000 movie level conversation. These cover summaries, character reasoning, scene understanding, and much more. And so finally, the LLaMA model achieves the state of the art results across all benchmarks, both on video and the image based tasks, proving that this method is not only efficient but also very effective. Okay, so in this slide, we will dive into some past LLM models and how they used to address the videos and what they used to do and where they lack to process the long video. So let's start. So basically, we have earlier we and we still have visual language models like Splip, Blip2, and Lava, who combine image understanding and with language generation. So basically, they work well on images and short clips, handling tasks like captioning or visual question answering. But when moved to long videos, these models break down. Each frame can generate hundreds of tokens. So a full video results in millions, which LLMs can't handle for sure. Some methods try to compress the input or pick keyframes, but they often lose important visual context. So don't scale to longer situations or durations, we can say. Basically, so this research paper addresses this exact challenge by introducing much more efficient way to represent a video frame, which will be explained in the next slide. Okay, so in this slide, we are discussing the overall architecture of LLaMA with so this slide and the next slide also. So basically what we input in this. So basically this model accepts either a single image or a video frame and user gives a text prompt or question also. So basically what step one is visual encoding. Here transformer based visual encoder like EVA-G extracts batch level embeddings from each frame. And the second step is basically of text decoder, where it converts user input into text guided queries. And queries are designed in such a way so that they can interact with the visual features which we grab from the frames. And the step 3 is token generations. So since we get both the text and the visual, so now we will generate the tokens. So first, as we discussed, the context token and the content token. So what the context token is generated using cross attention between the text queries and the image embeddings, captures instruction relevant global context, and the content token extracted by adaptive pooling from visual embedding and retains frame specific visual content. And here we have step 4, which basically projection of the tokens. So both the tokens are linearly projected into the LLM combating embedding spaces to check the what we say we used to do the dot product between the two vectors. So it is the same thing like here. We just find the relationship like how they are related to each other, and we try to make a token from the most relatable projections. So in step 5 is language model output. Projected tokens and user prompt are passed into LLM. And LLM generates natural language responses. And here we have shown the visual of all visual also of our LLM model. So this is how it works. So let's jump to the next slide. Okay, so in this slide, we focus on how the context token is generated. So the goal of the context token is to summarize the most relevant visual information in each frame based on users' instructions. So let's see how it works. So basically the model uses the text decoder to generate a set of queries from the user input because it would be required to generate the context token. And these queries are then matched with the visual features extracted from the image using the mechanism called context attention. In simple terms, the model asks which parts of the image are most relevant to what the user is asking. So basically the most similar uh, dot product kind of two vectors. Mathematically, it implies between the queries and the visual features and takes the weighted average of the important regions. This becomes the context. This is what we call context embedding. So this embedding is then projected into token that's compatible with the language model. So what makes this powerful in that context token changes depending on the question. For example, if the user asks about animals, the model focuses on animals. If they ask about weather, the it shifts from to clouds. Basically shifts from animals to clouds or sky. So as shown in the paper's attention maps, this mechanism gives the model the ability to dynamically adapt to different instructions and capture only the most useful information per frame. Okay, now we will look at the second part of the dual token design, which is the content token. While the context token captures instruction relevant information, the content token summarizes the actual visual appearance of each frame. To do this, the model starts with visual embeddings produced by the encoder. Then, instead of using all patch tokens, it implies adaptive average pooling. This compresses all the patch level features into a single embedding or smaller number of them, depending on how many tokens we want to keep. So in the case of long videos, as LLaMA width typically keeps just one content token per frame to stay efficient. For image stars, it can use more tokens like 567 or something to retain richer spatial details. After pulling this content embedding is linearly projected to match the language models is token just like the context token. So what's great about this? So we can ask like what's great about this design in flexibility? So basically, is it flexibility which makes it most uh, impressive design. The model can dynamically adjust how many content tokens to use based on the available computer budget or the complexity of the input. So it depends on us. So overall, the content token provides the raw visual details, while the context token guides the focus, and together they form a highly efficient and informative representation. We can say that. So now we will discuss the training strategy of these LLM models. So this model is trained in three stages, gradually building its ability to align visions with language and follow complex instructions. So the stage one is basically modality alignment. In the first stage, the goal is to align the visual features with the language space. This is done using the image video caption pairs over like 538K from CC3M and 238K from WebVid. Only the projection layers are trained here. The visual encoder and text decoders are frozen. This stage ensures that both visual and the text inputs are mapped into shared space the LLM can understand. In the stage 2, the instruction tuning. In this stage, the model learns to follow natural language instructions. It is trained on a mix of 625K multi-model QA pairs, 40K text-only conversations from, yeah, we can like share GPT, and 98K video QA examples. This is where the model starts to understand user intent and generate user useful responses. All modules are trained now except the visual and the encoder, which we will discuss in the stage 3, which is long video tuning. So the last stage, which is long video tuning. So this final stage targets the long video use case. A special dataset of 9K movie level QA pairs was created using MovieScript and GPT-4. It includes plot summaries, characters, reasonings, we can say scene analysis, many more of things also. At this point, the model is able to handle hour-long videos using up to 64,000 tokens. Yeah, which is impressive for such a small token per frame budget. So we can say that together these all three stages progressively teach the model how to align, understand, and reason over visual content in a highly efficient way. Okay, so in this slide we will discuss how this data set is created or on which this model is trained. So to help the model understand the long videos, the authors created a custom instruction dataset focused on the movie level QA. They use the MovieNet dataset, which contains over 400 full-length movies with scripts, as we mentioned here, and summaries also. They were used to generate high-quality question answer pairs. To automate this, they also use some models like GPT-4 and Claude 2, which produces diverse and natural sounding instructions across four categories. So let's discuss the types. So first we have summary based quiz. These basically ask for short or long plot summary. Example, summarize the plot of the movie. Okay. And the plot understanding analysis is the second thing type of instruction, though these questions test the model's grasp of major events and decisions. Example, why doesn't Rose get in the lifeboat? Yeah, important question. And so the third thing here is we can say So the third thing here is character level reasoning, which focuses on personalities, motivations, and relationships. So it can address the question like, what is Jack's personality be like? Okay. And scene level details, the last one. These target specific visual movements or background actions. Like we can ask here is what is Rose doing in the halfway scene? Okay, so these are the results which we get. In total, the dataset they have which they have created includes around 15,000 QA pairs, including which has 1K summary based, 4K plot level and 4K detail level and QA pairs, and the 6K from large scale basically instruction set. Okay, we can say that. So this dataset is key to making the LLM bit strong at both understanding the complex narratives and answering the detailed visual question across whole long video. Okay, so in this slide we have shown some evaluations and benchmarks datasets which has been used to evaluate this model. As you can see, for the video based benchmarks we have several things here like MSVDQA, which includes short clips with a question answering task, MSR VTTQA, which includes large set of diverse videos with open-ended questions, and the third activity net QA, where human activity videos like real world tasks and it has to analyze that video. Ego schema, it comprises long form egocentric videos for contextual reasoning to understand how well the model can understand the context of the video. SSV2, something something V2, we can say this. It includes the common sense question which we can ask from the model so that like we can understand how well it understands this video. So, similarly, in this slide, we have showed some benchmarks which has been tested, on which the model has been tested for the image. So basically, we can say image-based benchmark, which are listed here, as you can see. GQA, which includes real-world visual reasoning, and you can see the others also, and you can check out these you can learn about these from the internet also. So let's move to the next slide. Okay, so now time's come for the results. So like we have set some benchmarks to test our models, and these are the results which are provided by the model. This is LLaMA weight. As you can see, the LLaMA weight outperforms SOTA on video QA tasks, which is quite amazing. So as you can see, these are the accuracies which the LLaMA weight, and it is like more quite similar to BT adapter in this MSR VTTQA question, and here also it is quite same with the BT adapter, but here it manages to, in the first part MSVDQA, these type of question pairs LLaMA performs quite well, and basically in all the benchmarks LLaMA it outperforms all the previous LLM models. And as you can see, our generative evaluation benchmarks results, the correctness, detail, context, temporal, consistency, everything, out of which the LLaMA provides very good results here. And these are actually very good numbers as compared to other language models. As you can see that on the SSV2 dataset, accuracy of LLaMA weight was 20.12, while the video ChatGPT was only 11.59, which is basically a significant jump towards the accuracy. And as you similarly you can see in the ego schema for the long video QAs, LLaMA would score 41% accuracy all the time spans from whether you can say 10 frames, 180 frames, 100 frames, any. So it was overall average score was 48% accuracy, which is very good thing.
So, hello everyone, I am Akanksha. I am currently pursuing BTech in Data Science and Engineering from IIT Mandi. And now I will continue the remaining slides. So, as you have seen previously that LLaMA vid is specially optimized for long videos, but it also performs extremely well on image-based tasks also. We will check here. So here each image is encoded with one context token and 576 content token. same as the LLaMA's 1.5 baseline. And you can check results here. So on GQA, which tests spatial reasoning, LLaMA's would score 65%, which is really better than LLaMA's, that is 63.3%. And even on VQAV2, a well-known dataset for image question answering, LLaMA's with matches LLaMA's strong performance with 80% accuracy. So I want to say that this result shows that the LLaMA's with dual token approach is not just efficient, but it is also effective across modalities. So even though it was designed for long video understanding, it also generalizes very well to static images too. So in this slide, we'll study that how important each of the two tokens, that is context and content, really is. So the evaluated the model under three settings. First is only content token, second is only context token, and third one is like using both tokens together, which is really default. And you can check results here. So I want to say that while both tokens perform reasonably well on their own, using them together consistently produce the best result. So this validates that the dual token design context token help with instruction alignment and content token preserve the actual visual detail. So the two token strategy is not just efficient, it also essential for performance as well. So in this slide, we will explore the trade-off between accuracy and token efficiency. The idea is to test how performance changes when we reduce the number of content token. And you can check results here. So with 256 content token, adding one context token boost GQA accuracy from 61.9% to 63%, as you can see here. As the content token drop just one per image, performance only slightly drops but remains surprisingly strong. So the context token plays a major role, especially when content tokens are limited. And even at extreme compression, the model performs very well here. And this shows that how flexible and efficient the architecture is. User can adjust content token based on computational budget. So in this slide, we will compare different text decoders used to generate the context token. The idea is to understand how much impact the quality of text decoder has on the final performance. So some of the variant tested are no decoder means no context token at all, but which is a small randomly initialized transformer, and Q-former is basically a pre-trained transformer used in models like PLP2. So you can check results here. What are the results of this? So in the conclusion, I want to say that this confirms that it uses a strong instruction aware text decoder like Q-former, which greatly enhance the model's ability to produce useful context tokens. So the model doesn't just need fewer tokens, it also generates better token, especially when guided by language. So in this slide, we will basically examine the latency or processing time or different components in LLaMA VID, which is important for real-time and large-scale applications. So the experiment was done using an NVIDIA A100 GPU and measures the average time taken per video frame. So in this, we have used two main modules. First one is text-free module, which basically include visual encoder and context token generator, and they are responsible for the bulk of runtime. And second module is like text related module. This basically include text decoder and context token generation. And with this you can check that result. With the BERT decoder, the total time per frame is around 5.17 second, and for Q former it is like 5.98 milliseconds. So importantly, the text related modules account for less than 20% of the runtime. So this shows that even through LLaMA VID uses dynamic instruction aware tokens, the overhead is minimal and most of the time is spent in the visual encoder. It means that the system remains efficient and scalable even for real world video analysis. So in this slide, I will present some real world examples that show how well LLaMA VID performs in practical settings. First example of like Zootopia trailer. If user prompt what's the name of the movie in this video, so model will respond. The movie described in this video is Zootopia. So it can also answer follow-up questions like who produced the movie or what type of movies is this. So overall, I want to say that the model is capable of identifying the genre, producer, and characteristic all from the short video clip. And if you want to check, you can check with this example also, example number 2. So on this slide, we will dive into attention map producing during the context token generation, which will help us to understand what the model focuses on when processing frames. LLaMA VID generates the context token by focusing on most relevant visual regions in each frame, guided by users' interaction. So for example, if the user asks about elephants, the attention map highlights the elephant's head and leg in the frame. If the user asks about a fishing village, the model will focus on boats, buildings near water, and seagulls. So this visual attention heat maps gives us insight into where the model is focusing during the reasoning process. For instance, for the prompt, what tall animals are displayed in the background? The attention map highlights giraffe, trees in the frame. So this attention map proves that the model isn't just blindly processing frames. Instead, it's dynamically aligned the most relevant spatial features with the user's intent. This makes the model explainable as we can visually verify which area of the image it considers important. So in this slide, we'll discuss about its strength. LLaMA will stand out for its efficiency and performance. It uses only 2 tokens per frame, making it possible to process hour-long videos with standard LLM models. And the context token is instruction aware, so the model focuses only on what matters for the user's question. And it is also generalizable, working well on both videos and images and across different LLM sizes. Despite its simplicity, it achieves state-of-the-art result on multiple benchmarks, and it is also open sources and lightweight. So overall, I want to say that it is fast, flexible, and accurate, a rare combination in vision language model. So we finally came to slide about its limitation and future work. While LLaMA vid is highly efficient, it does a few limitations. Firstly, using only one content per token can cause loss of visual details in complex scenes. Secondly, the LLM processes tokens sequentially, so it cannot do deep spatial reasoning like vision specific models. And third one is like the model relies heavily on pre-trained modules like QFormer and large instruction dataset. And for the future, the author suggests that hierarchical compression to preserve detail when needed, visual memory fusion to bring back spatial richness, and domain specific time tuning for areas like medicine or education.
Okay, last but not the least, in this slide, we will conclude our discussion on this research paper discussing the LLaMA paper. So, it is actually a very powerful method. What it does, it basically proposes a dual token representation where we were representing each frame with only 2 tokens. One is context token and the other is content token, as we discussed about them in the previous slide also. It also enables, like, which is a very big task, hour-long videos understanding using existing LLMs without increasing much computation, without changing the overall architecture of the current LLMs. It just finds a quick way to understand the long videos also. So the key takeaways here is it is very efficient since it only performs 2 tokens per frame for videos. We can, when we are just analyzing the images also, we can generate more tokens also as per our needs, and powerful. It basically outperforms state of the art on multiple QA benchmarks, as we have seen in our previous slides also, the results which the LLM bit gives us. And third, scalable works, as we can see, it works along images, short clips, full video length movies, and yeah, exactly. So on these is highly scalable and practical since it's very lightweight, as I said in the earlier also. It is very lightweight and trainable on standard hardware. So basically, the main thing here was changing the number of tokens required to analyze a single frame. So this was the very crucial step in this model. Okay, so we would like to end our video here. So I hope you like this video and you had understand some concepts, and it helps us you to understand the research paper also. If you have any questions or doubts, so you can comment below in the comment section. Thank you.